So our next speaker is going to be virtual. So it's my pleasure to introduce you Lucas Black, who has worked in academia and biotech for the past 20 years, with over a decade specializing in flow cytometry. He leads a team in the in vitro pharmacology department at UCB and runs a small flow cytometry consulting practice. Outside of work, he has always enjoyed exploring large datasets and began collaborating on gender representation in flow cytometry after a conversation on LinkedIn. Thank you.
Hi, everyone. So I hope you can hear me, and I just want to say thank you to the organizers for having me on. And yeah, I just want to, can you guys hear me?
Yeah, sorry about that.
Sorry, I just had a note come up. Great, let's move to the next one. So just want to start with some acknowledgements and some conflicts of interest. I work for UCB. They have not seen any of this data. It's not for it's on the bottom right hand side here. Also, I'm really not the driving factor for all of this research. It's all actually being driven by Fabian, and her real interest in actually how gender is impacting people in work and in clinical flow cytometry. So it's really important, I think, to be working with amazing people who have this level of passion for their work. So what do we really mean when we say gender? There's a lot of words on this slide, and I really want to sort of focus on the fact that gender is not sex and sex is not gender, but they do interact with each other. There's a full definition in the box at the bottom if anyone wants to read it. But for this talk, what I really want to talk to you about is inferred gender. So whenever I say gender in this presentation, I actually mean I have used an algorithm to look at a lot of data about people and try and guess their gender from that data. It's absolutely not perfect, but it's the best tool we've got with these very large data sets. And also, just to be super clear, inferred gender is not gender, and it is not gender identity. So across the whole talk, when I talk about females, I'm always going to have them in purple, and males will always be in orange. When we're doing the gender inference, we don't always get it right. So I've got a large proportion of people who are in gray, and those I'm unable to assign gender to. So why do we really want to look at gender in flow cytometry? And the real reason is many of you will be paid your salaries based on the publications you've published. Like, we get data out, and that's really important. So if you are in a network and your position is based on gender, we would like to know that, because ultimately it leads to your jobs, it leads to better publications, and this inequality in publishing is well described across multiple other fields. So our aim is to systematically examine gender disparities on the global flow cytometry network and see if these structural positionings are collaborative or not. Our hypothesis that we're going to test, and I'm not going to be able to present all of the data today, is that females occupy fewer central roles, have smaller collaboration networks, and are underrepresented in these highly connected institutions. So where do we get all of our data from? Well, we started this process by using PubMed, and PubMed is amazing. But along the lines, we found OpenAlex, which is the Open Library of Alexandria, and they have over 450 million works. So that covers everything from books, articles, reviews, patents, some patents. And they have 106 million authors. So using that database, we search for the term clinical flow cytometry in titles, abstracts, and keywords. That led to a 1.2 million works and just under 3 million unique and disambiguated authors. When we look at the primary field for these authors, medicine is right on top at 37%. Biochemistry, immunology, agricultural sciences, they're all there. These are the kind of fields we would expect when we are seeing people who are publishing in flow cytometry, but also clinical flow cytometry. Right, so on to these gender algorithms. And inferred gender is incredibly complicated. Like, it's making a lot of assumptions, and every one of the tools that I can use that are out there is bias. They all are biased in slightly different ways. So what we've chosen to do is test 18 open source tools. And we tested these against 13 data sets in 7 languages. One of the largest data sets happened to be in Chinese, but we knew that the genders of every one of the people or any one of the names that was in that data set. So we basically ran them across and we weighted the accuracy based on what the data was and how big it was, and the F-score is weighted against the data set as well. So on the bottom left-hand side, you can see all of them are clustering together, and that is because these are not amazing at scoring gender in these Chinese networks. Gender computer up on the right-hand side here was selected because it actually scored a measly 0.25 on Chinese and Russian, but it's so much better than every one of the other tools. It scored pretty well on English and Arabic. It even scored better on Arabic than some of our this Persian gender detector. So even the specialist tools aren't always as good as some of the more generous ones. Quick note, gender detector did actually score better in English names than or Western names than gender computer. But as described by this very large bubble, it actually takes a lot longer to run. In fact, I can run all of the other gender inference tools on all of the data sets before gender detector finishes. And when you're dealing with 3 million names, speed really is important to us. So we went with gender computer. The network as a whole, there's 2.8 million people. We see that males make up the majority, so 41%, 35% are female. And it begs the question of why do we see this gender difference, right? It's an imbalance that we shouldn't really be seeing in a network going on. And the reality is the network is so large, it's over a 50-year period, 51 years. We can actually see that the male dominance actually dates back quite some time. So in 1975, if you were working in the flow cytometry field, there was only a 16% chance that you would be female. In 2025, which is my last year of data analysis, that has now risen to 48%. So in terms of pure numbers of people working in the field, gender equality has really reached as close to parity as it's possible for me to measure. I'll go one step further. When we start looking at entry cohorts, so if you are a person entering the clinical flow cytometry field in 1975, you had just over a 25% chance of being female. But by 2005, it's back to 50%. So from 2005 to 2020, there have been more female authors entering the clinical flow cytometry field than there have been male. So in terms of progression in careers, this is great news across the board. So it really does look like success. Like in 2025, 50% of females are 50% of authors are female, and the cohort parity really does favor female authors coming into the network. But what if this isn't the whole story? What if female authors and male authors are actually occupying different networks? So on the left-hand side here, this is just a snapshot of the network from 2020 to 2025. And in the center, you can quite clearly see a large mix of these orange nodes and these purple nodes, and it's quite a mixture. But on the left-hand side here, you've got this male dominant node, and then you've got this female dominant node to the bottom. And what we were starting to notice when we were doing the analysis was that really there's the possibility that males and females are actually occupying different networks. Right, so one of the things to sort of ground everyone in is to sort of understand what we mean when we're talking about networks. A network is really just a way of describing two things that are connected. In the network parlance, we talk about nodes, and nodes are, in this case, authors, and the edges between them are how they're connected. And in this case, it's a shared paper. So, for example, on the bottom here, we see author A shares a paper with author B, and we simply draw a line between them. That's basic of all networks. They get slightly more complicated. So on the right, we see authors A, B, and C. Authors A and B, they share a couple of papers, and they've got a relatively thick line. Author B and C, they only share a single paper, so their line is thinner. But authors A and C, they share more papers, so the line gets thicker, and that's how we can talk about it and present it. So looking at authorship and going into how we can adjust this to our real world. Here I am outside of a restaurant in freezing cold weather in London, but I went to school with this guy called Chris Rankin. And I don't know if you noticed, but that's Percy Weasley. He is in the Harry Potter movies and works with Marion Margulies twice. Marion Margulies has done this movie with Kevin Bacon, who is incredibly well connected across all of Hollywood. There's the Oracle of Bacon website was a bit of a smash in the early 2000s, and everyone talked about 6 degrees of separation from Kevin Bacon. And this is how I am 6 degrees away. I'm actually 3 degrees away from Kevin Bacon. But most people are like me, and most people have these small networks. So here's my publishing network. And as you can see, I'm a small red dot in the center, surrounded by other people who have better connections, they have more connections, and they're more interesting. So there's these small number of people, and they're like Kevin Bacon, and they have these really big networks. And there's the big Kevin Bacon of our field is a professor in Salamanca, and here he is in the middle of his network, and it's just incredibly well connected. There's structure here that is really easy to see, but he is what we would call a key opinion leader or someone with a high network centrality. So these are the network centralities that we're sort of really caring about in our analysis. So what are these network centralities? And we're going to talk about 5 of them. There are many, but the 5 that are most important for this talk are degree centrality. And this is how many collaborators there are. So essentially, every edge coming into a node adds 1 to the degree. Then there's betweenness. These are people who sit in structurally important positions in the network, and they are essentially between 2 parts of the network, holding it together. There's closeness centrality, and these are the people who allow information, data, access to sort of travel through the network, and they're really important to sort of facilitate the world around them. We have PageRank. PageRank is really famous because it's the Google algorithm. And it says, I am well connected and I'm connected to other well-connected people. So it's like the friend of my friend is very important, therefore I am important. And then we have eigenvector. Eigenvector is a little bit more hard to get your head around, but essentially it's about quality and importance of these connections, not just the number of them. If you're a key opinion leader, you are high in the majority of them, but always high in centrality, betweenness, degree, and eigenvector. So on the right-hand side, I find it very useful to look at the network in this way. So here it is in its entirety. It doesn't quite fit on the screen, so we've squeezed it down. There's 670,000 nodes. So that's a much smaller number than the 2.8 million. And the reason it's much smaller is we've done a level of filtering. We've removed everyone who only has 1 paper in the network. And that's mostly to do with the ability to actually perform calculations and visualizations. Of those, there's 4 million edges between these co-collaborations between authors. So it's a really well-connected network. Because of the richness of the OpenAlex database, we have been able to either directly use or calculate over 200 metrics per author. And these include their name, the country, first publication dates, last publication dates. We have their whole network and where they sit within this network on the right, but also where they sit within their own ego network and all the metrics that come from that as well. So we've got a very rich data set. Okay, so gender homophily. Gender homophily is how likely someone is to collaborate with someone else of the same gender. And we score it from 0 to 1. But to sort of give you a sense of the scale of things, what we have here is betweenness, and we've got a lot of authors in the network, but there's only a handful of these dots. The professor for Salamanca is this big orange dot here. When we look at degree, we can see actually there's more of these nodes. They become bigger and they have higher degree. So it's much more spread out, but still you can see there's only really a small number of people who have high degree. Homology, gender homophily, sorry, is a completely different story. There are so many people who have only ever collaborated with people of the same gender that we can no longer see any structure within our network. So it's really quite an interesting proposition of this network. When we look at gender homophily, we can plot it in a different way. So on a scale of -1 to 1, 1 being I only work with males or only work with the same gender, and -1 meaning I only work with the opposite gender, we want to be around 0. That means we're working equally with all authors. What we can see here is on the left-hand side, female authors actually collaborate relatively uniformly, slightly more with the opposite sex. Male authors, on the other hand, they are a majority collaborating with authors who are of the same sex. So we've got this sort of disparity, like female authors are less, have lower homophily than male authors. Right. So when we plot the data slightly differently, we can see that there is no gender authors, no same gender authors on the right-hand side, and only same gender authors on the left. And we kind of expect to see this bell curve because actually most people would be working with males and females across the board. But what we actually see is on the left-hand side here, that 12% of authors are not working with anyone of the same gender. So essentially what we're saying is if you're a female in this network, and the majority of that part of the network is female, that they only publish with male authors. The reverse is true for the other side. Like in this part where they only are working with the same gender, it's essentially males saying, I only work with other males. So there's this real disparity in the network about who we are and who we aren't working with. We have a question, and I don't think we've got to the bottom of this question just yet, but is this a question of a question of choice, or is it a question of no same genders actually being available to work together with? And we haven't got to the bottom of that, so it's definitely an ongoing question for us. So when we look at our data, we have huge numbers. Like looking at 3 million, practically any stat I run is going to be significant. So we can basically all of my p-values are 10 to the minus 11, and it's just incredibly difficult. So one of the things we do is we look at Cliff's delta. And the way I like to think about this is either looking at stain index and shifting how that looks, or perhaps looking at Stokes shift and how those two spectra just spread apart. And that's what we're looking for. So we have a much more complicated picture when we look at the Cliff's deltas between our networks. So on the left-hand side, we can see that betweenness is actually a male advantage. It's a small advantage, but it's a male advantage. On the right-hand side, we can see PageRank. That's the Google algorithm, is actually a male advantage as well. It's our strongest male advantage. But in the middle, we've got closeness and eigenvector, and these are female advantage. So these are relatively small advantages, and it's good to see that we're not telling a single unified story that, men only are working with men, females are only working with females, but it's much more nuanced, much more complicated than that. The next sort of question we wanted to look at was into how it impacts the progression across a career. So because we know when these authors started publishing, we're able to sort of stratify them out. And we've come up with 5 groups of authors. There's early stage authors, and they're sort of the postdocs, the late PhD students. They're publishing their first couple of papers, so they've only been in the network for 1 or 2 years. Then we've got our mids career who've been in up to 10 years, established up to 15, and going all the way to veterans who've been in the network for over 20 years. These are our proper PIs. These are the professors and the people who've been doing lots of work for a long time. And the interesting thing that we can see is a degree is a great example. Females start off on the right-hand side here with this advantage in degree, an early stage of their career. But as their career progresses and they become more and more senior, that female advantage gets smaller and smaller and then flips into a male advantage. We see that across for eigenvector, betweenness, and closeness. Closeness doesn't quite flip, but it gets quite close. Page rank is always a male advantage across the entire career span. Again, this is a question we haven't been able to dig right into the details of yet, but it's definitely an interesting finding. So we want to be a little bit more nuanced against this as well. And we took the idea of a career and broke it up into these archetypes. And we based our archetypes not on the network itself, but on things like the total amount of works, how many works an author is publishing per year, how many of those works are either first authorship, last authorship, or marked as corresponding author, their citation velocity. So did they actually publish a really big paper once and they got lots of citations really quickly and their career just took off? Or are they publishing less often? Output skew. Where are they producing all these papers all the time? Or are they publishing a handful of papers a year and then a handful of papers another year, but big gaps in between? And then because we want to look at retirement as well, we looked at their last publication date. And that came up with these authorships on the right hand, these authors on the right hand side. So going roughly in career order, we've got our single authors who we don't know much about. Then we've got low output early careers. So these are the postgrads and some grad students, certainly my grad student life. Then you've got into moderate outputs, and these are sort of early career sort of PIs or on their way to being PIs. And they're either collaborating a lot or they're sort of emerging out. There's a special kind of moderate output author, and they're independents. They're the ones who really don't collaborate a lot. They collaborate a little, but mostly publish 1 or 2 author papers. Then there's the high output people. And these are your key opinion leaders, your big professors. They're the ones who are shaping the field. And they come in a number of flavors. There's the high output collaborator. They're collaborating with everyone all the time. And then you have the high impact people who are just going for it. They're collaborating with everyone, and they're generating those really big science, those really big nature papers. So we've got these archetypes. We wanted to make sure that the archetypes are real. So we took other metrics to look at them, and we can quite clearly see that traditional bibliography metrics like H-index, like I-index, they are actually correlating well with these archetypes. So high output, high impact PIs, they're really high in H-index and I-index scores. Low output authors, they're low for it. But they're also, this page rank actually correlates quite well, as does betweenness and gender homophily. Gender homophily is this slightly lighter line in the center that's not as correlative. It's much more, it's only got a p of 0.02 and an r-squared of 0.5. So it's not the highest correlation in the world, but it's still suggestive. When we look at these outputs and how gender homophily is expressed within them, we can see that high impact authors tend to be male dominated. So the high impact PIs, they're 70% male, established PIs 70% male. These moderate outputs, independent PIs, 70% male. Lower prestige positions tend to be female dominated. So low output early careers, female dominated. Low output retired, they're female dominated. Moderate output steady collaborators, female dominated. When we overlay the gender homophily scores of this, we can clearly see that if you are a high impact prestigious author, you are more likely to have a higher gender homophily. So in the previous slide, when we're looking at gender homophily, we could see that all males were 0.2 and all females were sort of negative 0.1. So even though there's a high proportion of females in this group, they're still showing really high gender homophily across the entire board. So this 0.17 is probably a very high number when we take into account just the male authors. And really, I guess what I want to say here is this is what I like to think of as the old boys club. These are authors who are in the room, they've been in that room for a long time, and they don't necessarily know that they haven't opened the doors to everyone, but they're not really interested in opening those doors to everyone just yet. There's some female authors who are coming into that room, but essentially it's a very difficult room for them to get into. And that's impacting their structural career and their positions within the network. So I know this has been a whirlwind. So just to sort of summarize, gender parity in terms of the clinical flow cytometry network has been met, and it was met 20 years ago, essentially. But it's far too simplistic a way of measuring our individual influence and long-term trajectories within our careers. The work that we've shown very briefly here today is a comprehensive network analysis of gender bias. It shows that there are structural biases within the network, and we can measure those. It means that we can actually say that gender homophily is prominent within highly productive authors. So these are your key opinion leaders and the really important people who are publishing in science. And these network positions change over career, and they gender favors or disadvantages fluctuate over time. We really do need to sort of understand these connections and how they influence opportunities, and actually build in long-term strategies to get people on the correct career paths. Like everything that happens in our network is a decision. So we can use this information to help shape people's careers and get them into that room, and get them into that room earlier in their career. But we also need to sort of call out and say, actually, there needs to be a lot more studies along these lines. There needs to be understanding of how to actually generate these data, whether it's geographical regions that are specifically good at this or geographically regions that are poor. Is it institutions? And we're hoping that our approach here is going to be a blueprint to sort of those further studies. And I think I'd like to open up to questions.
Do you have questions? Questions? I'll start with a question. Have you looked kind of, I guess, not just across that entire period, but sort of like changes throughout the period of publication?
Yes, we have. And quite honestly, it's a lot better now than it was in 1975. Quite a lot better now. But yes, we're actively looking into that field, yeah.
Okay, if we have no more questions, thank you very much, Lucas, for your talk. That was really interesting.